you already for reading that long title. I'm Julia from the NMI in Reutlingen, Germany, and my background is in regenerative medicine. And what was striking me for the last years is that even though tissue engineering and the approaches that are applied here are quite advanced and also not that new, there's still a very poor market access of these strategies. So there's up to date just 2 or 3 tissue engineering approaches commercially available in the clinics. And this comes along with some bottlenecks that we still do have to face, which all come along in the overall assumption that we do need to get a better understanding of the interactions between our materials and the cells. And what I'm mainly focusing on is how we can improve that understanding by, for example, getting new methods for cell material interactions, but also in vivo follow-up. But here I want to focus on how advanced in vitro models, which you're all familiar with, combined with spatial resolutions, especially targeting tissue dynamics, can help us to advance these techniques. I think this is something I do not need to repeat in that session. Often with conventional methods, we just have a snapshot of processes that happen in our system, and as all of you over here create these wonderful in vitro complex MPS models which allow us to do dynamics which recapitulate the human physiology in vitro, we wanted to combine that with in situ imaging techniques which are label-free, so we do not need to apply any dyes, which also means no extensive tissue preparation, which our goal is then to identify novel biomarkers. The techniques that we are establishing in our lab are 2 laser-based techniques. On the one hand, Raman microspectroscopy, which is, as I said, a laser-based technique, and due to the interactions of the photons of our sample and the molecules of our sample, we do generate a spectrum, which we also consider as a molecular fingerprint of our sample. We can either do that as single-point measurements, but we can also scan an area and recreate images with that. So here we use the molecular composition of a sample to visualize structures. On the other hand, we use fluorescence lifetime imaging microscopy, which is based on the fluorescence of the samples. We mainly apply that on endogenous fluorophores, in our case especially NADH and FAD, and instead of looking at the intensity of the fluorophore, we look at the lifetime of the fluorophore, which can guarantee or give us access on metabolic processes that happen in the cells, such as glycolysis, oxidative phosphorylation, or also oxidative stress. We did not start with these technologies right in chip, so we first had a look at tissue samples, tissue sections, similar to histopathology, but just that you get a feeling on how these images can look like. So those are all false color-coded images. We do not need any fluorescence tag or dyes. This is just due to different molecular or spectral patterns that the sample emits. And we cannot only generate these nice images, as we do have in every pixel an underlying spectral information, we can also further dive into the underlying spectral information or molecular composition, which I want to point out here in a study which was just recently published by one of our PhD students who investigated fibrosis. Normally, fibrosis is just characterized by the huge deposition of collagen fibers and can be done by immunofluorescence or histopathological stainings. And similar to that, Raman imaging without the application of any dyes can also visualize that structures. However, those fluorescence markers just identify the collagen fibers, and our question now was whether there is a difference in fibrotic collagen fibers versus healthy collagen fibers. And this is what we did then. We went into the underlying spectral information and could actually identify small differences in the amino acid composition between fibrotic collagens and healthy collagens to further follow up in tissues, for example, which have already a high expression of collagens natively, such as, for example, breast tissue. This does not only work in tissues, we can also monitor at the subcellular level. So for example, here we wanted to do phenotyping of the polarization or the activation of macrophages. At that stage, just single cells in vitro culture, and this is such an image of a single cell. We can break down the major subcellular structures. An example here, lipids, proteins, nucleic acids, as they do provide slightly different spectral signatures. And what we were then further interested in is whether within the overall composition of one of these substructures, in this case we digged in further into the lipids, we can identify different macrophage subtypes. And what was shown here is that indeed, especially in the lipid signature, there was a difference in the saturation or oxidation stages of triacylglycerides, shown in the different spectral patterns between inflammatory and anti-inflammatory macrophages. We tried then to go back and translate that into the tissues. For single cells, it is quite easy to target them because there's just media around them, but what happens if we go into a more complex tissue environment? So we have shown that ECM structures are visualizable, but how about cells? So we use those macrophage patterns to go into tissues where we also have other cells around, where we also have other proteins around, and try to combine or compare the sensitivity of our Raman approach, which you can see in the right column, to basic immunofluorescence imaging of surface markers of macrophages. And what we could show over here is that there were similar ratios visualized by images that were just generated based on the spectroscopic analysis compared to tissue sections that were processed by immunofluorescence imaging. So can we also do that in 3D? Yes, that works. So for organoid or spheroid samples, both Raman and FLIM can generate these images. And as I already spoke a lot about Raman, I quickly want to give you an example on FLIM imaging, as this is highly sensitive to metabolic processes. We explored here the sensitivity to track the metabolic response of patient-derived tissue models. So patient-derived cancer tissues, where based on cytotoxicity assays, we did already know that they have been characterized as resistant or responsive donors. And here you do see FLIM images, so metabolic images, again, false color-coded images based on the metabolic portfolio of that spheroid or organoid. And what we could observe over here is that whereas in resistant patient-derived tumor models, no big change happened upon drug treatment, we did see that on the one hand already the non-treated samples did, for some of the FLIM parameters, already showed slightly different metabolic profiles, and that especially during the treatment, stronger effects also happened here. What we also could test is that different drug treatments do provoke a different metabolic response. So for example, different patient-derived organoids showed a different metabolic effect compared between cisplatin treatment versus venetoclax treatment, and that could also be monitored over time, as we can do these images of the exact same organoids at different time points, as this is not affecting the organoids. Good, so I will spend the last part of my talk into how can we now integrate these readouts into chip platforms. What can we access with these technologies? So we have different modalities. We can not only look at the tissue models, which can be a tumor tissue, but also any other type of tissue. But what we are also capable to do with that technology is to look on the one side on circulating immune cells or other cell types to target their activation and phenotypes in situ, so that can be done directly on the platform. And we can also just look at the effluent to see whether, for example, lactate or glucose levels are changing over culture time. There were a few posters happening, I think, Tuesday and Wednesday. Maybe you had the chance to look at them, but what our lab is currently working on to integrate these readouts in chips. So one idea is to monitor the tumor immune interaction. So we were able to identify a T cell specific Raman signature, which we can then use to target T cells in a cancer spheroid environment. The application of FLIM on the bottom left is again more in the direction of drug efficacy testing. So if we integrate a patient-derived tumor model, we can trace after a drug treatment the different metabolic changes over time and also individually do that for different patients. Another work that is going on a bit farther away from the cancer site is targeting host microbiome interaction, because also different bacteria do show different Raman signatures. So also here we can monitor the heterogeneity and the effects of bacteria on human cells. This were just quick example. I will guide you now once on the example of the pancreas on a chip, which a former PhD colleague did together with me in the lab, where we also try to implement these technologies. So the overall idea here was to have insulin-producing spheroids that could, on the long term, serve as treatment opportunity for diabetic patients. So together with the microorganol lab from Peter Laskill, that chip platform was established, which allowed to trap these insulin-producing beta cell spheroids and allow perfusion of different media. In our case, we wanted to test how these spheroids react upon glucose perfusion. This chip is optically accessible, so maybe that's also something worth mentioning. Raman is sensitive to a lot of structures, but of course it's also sensitive to your plastics of your microfluidic chips, so it's important to have an optical accessible chip, ideally having a glass imaging window somewhere. So this was facilitated here. And those were the Raman images that were generated once upon Krebs, which means low glucose medium, and then in the exact same setup, perfusion of a high glucose medium was achieved, and Raman images were taken at different times. Again, those are the false color-coded images of the major subcellular structures. We focused on lipids, mitochondria, and nuclei. Similar to fluorescence imaging, because the signal intensity of the Raman spectrum correlates to the quantitative amount of that molecule, we can do semi-quantitative analysis of the different structures. And we did observe an increase in mitochondrial activity upon glucose treatment, however not in the lipids. But as we do also have the molecular information underneath, we further went into the lipid signature using multivariate analysis and could see actually a separation not on the quantitative side of the lipids, but on the qualitative sides on the lipids, and we're actually able to identify lipid signature relevant to inositol triphosphate, which is involved in the insulin secretion of insulin-producing cells. Another question we had, as we do form these spheroids at a certain size, there is the chance that as they are so far not vascularized, they do form a hypoxic core. And this is something that is for sure not good for our in vitro model, but definitely not something you do want to implant into a patient later. So the question was here, how biofunctionalization could prevent hypoxia-induced damage on these spheroids. So the spheroids were cultured with a protein, nitrogen-1, and what was done again were the Raman images in this chip, so in living conditions. And what we could show is that with this biofunctionalization, for one, also the mitochondrial activity, but also the insulin content could be maintained in the core when the spheroids were subjected to hypoxic culture conditions, but this could not be maintained in the normal culture medium. The same observations were then also followed up with the fluorescence lifetime imaging, as this is a slightly faster technique. So here we can really take images every 5 minutes. So also here we looked at the ratio between long NADPH lifetimes and short NADPH lifetimes, which give us an idea on the ratio between glycolysis versus oxidative phosphorylation in the chip, and could in the future, for example, serve as a readout for quality control of these spheroids without destroying them. So you could directly sort them to use the ones that do show good properties for implantation, and the other one could be discarded. Good. This brings me to the end. I hope I could show you how non-destructive imaging allows for spatially but also temporally resolved imaging and can address different, not just tissue composition, but also cellular phenotype characteristics or metabolic activities. And shown here, so maybe that's a question that would arise, also the penetration depth of that technique is quite good in comparison to confocal fluorescence microscopy. So this is a bioink where we were able to penetrate up to 1 millimeter. And as I did not go into detail on that, but as mentioned, we can also monitor biofluids. So here, for example, lactate and glucose spectral intensities correlate to the content of glucose and lactate in a sample. And in the end, if you are more interested knowing more about that technique, I invite you to go onto that QR code link. This is a webinar which was organized by the 3R network and was broadcasted and is now saved here, where I will explain more about the technology. And the good thing is also Torsten Meyer's technology will also be explained in there, so you have 2 in situ monitoring at once in there. And in the end, I just want to thank my group in Tübingen and at the NMI, and also all the alumni that were involved in the study, and you for your attention. Thank you.
Thank you for your nice talk. And now we already start with the first question.
Thank you for this really nice talk. My experience with using Raman in microfluidic chips is that most of the polymers we've tested do interfere with taking the spectra. So there is a high range of the spectra which is being masked. So my first question would be, is there any recommendation from your side what kind of polymers are more compatible with Raman spectrometry? Because it's always time consuming. And my second question is, on your slide number 12, you have showed a couple of bacteria which you discriminated based on their spectra. I'm not an expert for reading these spectra, but to me they look very similar to each other. How long does it take to really predictively discriminate them from each other in such a chip?
Yeah. So in regards of the polymers, yes, that is a problem. We also have a PhD student that is now really fully characterizing all the different polymers that are used in chip to see for the bleed through. In principle, that technology is confocal. So if we have a defined depth or height of the chip, we are able to at least go through a plastic. And if your tissue sample is somewhere here, that's still to some way doable. But of course, if you do have a cell layer right attached to a polymer membrane, then we often have a high bleed through of the membrane polymer, and all of them have very nice spectra which highly interfere with the biological spectra. PDMS actually is, even though we complained about that in the beginning, because this was also done in the pancreas on a chip, is slightly better because there's a few defined peaks, but PMMA or TPE have various peaks which interfere. So here we definitely need to make a gap between the tissue to be analyzed and the cells, and it is possible in some degree, and ideally we do have somewhere a glass imaging window in between because glass is not interfering with the Raman. In regards of the bacteria, yes, there need to, it is all biological specimens. There's huge databases for Raman which comes from material sciences, unfortunately not for biomolecules. We are slowly elaborating on that. They still do look similar, so it's not that by eye I say that's that bacterium, that's that bacterium. You really need multi-rate data analysis tools, databases, machine learning to access these information and differentiate them. So that's quite some establishment, but especially on the bacteria side, there's actually quite a lot done, and I think people were even able to discriminate up to 20 bacterial species, not in chip, but in other applications.
Thank you, Julia. So we have another question in the back.
Thank you very much. Thank you for the very nice presentation. It's thrilling to know what we can do with Raman spectroscopy. I'm Hugo Salmon from Université Paris-Cité. My question is really related to the previous one. For polystyrene people, that is to say most of the people using material for cell culture, is there any strategy to overcome the styrene signature to make it possible? And you mentioned a hybrid structure where you have a bottom in glass and a top in a different material. Is it the only way to overcome it?
There is people that have tested to somehow with mathematical techniques to subtract these signals, but at least from our experience, the least plastic is in there, the better. Once, for example, we just target glucose, and we do know that glucose is what we want to target, and we're just looking for that specific peak, then it's easier. Then there's also signal enhancing techniques for Raman spectroscopy. This is all spontaneous, which we do when we have no idea of what is happening in there. If we target very specific molecules, then there is ways around of using plastic, but unfortunately, yeah, the more glass the better, or the least plastic the better.
Okay, so there's room for one or two more questions. So
yeah. Hi, Julia. Thank you for your talk. I have a question regarding your FLME analysis, where you analyzed the cancer organoids, if they're resistant or responsive. Maybe you mentioned it, I'm sorry if I missed it. But could you identify differences before the treatment? So could you identify even so predictive if they were responding or not?
Yeah.
And do you combine, or do you plan to combine this with machine learning, so deep learning?
Yeah, definitely. So I mean, this was more like a coincidence. We were rather planning on, okay, we do see how they react to the treatment, and our hypothesis was that the ones react more, the other ones react less. But when we then also looked at the control images before treatment, we were surprised that we even, I mean, maybe it doesn't make sense because there must be some reason why the ones are sensitive and the other ones not. But that was one of the additional finding we had in that study, that actually there is some differences between control, resistant versus non-resistant, which even allows us to predict an outcome much further before we have to screen various drugs, how they react to that. And that PhD student that was working on that, he started integrating first neural networks, also because there is so many different data and readouts you have to integrate here. This is not just visualized by one single plot. I just showed now representative images, but we are definitely interested in further advancing that with machine learning and neural networks.
Thank you. So there's another question, and please, a short answer.
Yeah.
Thank you. So actually a couple of questions. One of them is, I mean, you're addressing the concept of lifetime imaging, which, I mean, assumes that there's irradiation after irradiation after irradiation of the cells. I mean, I assume that some of the excitement you're doing is at fairly low wavelengths that can lead to some level of phototoxicity. Is that an issue that, I mean, are you observing any such toxicity?
Not that we are aware of. We use a multiphoton laser, so we use wavelengths in the near infrared laser range, which is also less cytotoxic
Okay.
than green lasers, for example. But there is studies that have investigated the toxicity, and especially for the fluorescence lifetime imaging, the excitation is below a minute. There have not been effects observed on the cytotoxicity.
Okay, because that would be my concern. And just another question related to then, this really reflects my ignorance on the practicalities of how you do this, but I assume that you need to remove the chip from the thermostatized chamber to put it into the stage of the microscope. I mean, that sequence of thermal shocks, it's not also an issue for the...
Yes, you can talk to my postdoc. She can tell you lots of story about that. And also, we do not want to occupy the microscope the whole 7 days. But yeah, maybe you find my postdoc in the break, and then she can tell you how she's tackling that.
All right, thank you.
Thank you.
Okay. Thank you, Julia, for the very nice presentation.